How do metamorphic textures form? Metamorphic textures form through the process of metamorphism, which is the alteration of existing rocks due to changes in temperature, pressure, and chemical environment within the Earth's crust or mantle. This transformative process typically occurs deep beneath the Earth's surface where rocks are subjected to intense heat and pressure over long periods of time. The formation of metamorphic textures involves several key mechanisms. Recrystallization. This process involves the growth of new mineral grains from existing ones without melting the rock entirely. As the rock is subjected to increased temperature and pressure, atoms within the minerals migrate and rearrange themselves into more stable crystal structures. This results in the development of larger, equidimensional mineral grains characteristic of metamorphic rocks. Neocrystallization. In some cases, metamorphic minerals may form entirely new crystals that were not present in the original rock. These new minerals often reflect the specific temperature and pressure conditions of the metamorphic environment. For example, the formation of minerals like garnet, staurolite, or kyanite is indicative of specific metamorphic conditions. Foliation and lineation. Foliation refers to the parallel alignment of mineral grains or the development of preferred orientation within a metamorphic rock. This alignment typically occurs perpendicular to the direction of the greatest compressive stress, resulting in planar structures such as slate cleavage or schistosity. Lineation, on the other hand, refers to the linear arrangement of mineral grains or other features within the rock, often reflecting the direction of tectonic forces during metamorphism. Porphyrblast growth. Porphyroblasts are large crystals that grow within a finer-grained matrix of other minerals during metamorphism. These crystals often exhibit well-defined crystal faces and can grow to sizes visible to the naked eye. The growth of porphyroblasts is indicative of specific metamorphic conditions and can provide valuable information about the intensity and duration of metamorphic processes. Pressure solution. Pressure solution is a process in which minerals dissolve at points of contact under pressure and recrystallize in areas of lower pressure. This mechanism contributes to the development of foliation by promoting the growth of minerals perpendicular to the direction of maximum stress while causing dissolution and reprecipitation parallel to the stress direction. Metamorphic reactions. Metamorphic reactions involve the chemical transformation of minerals into new phases due to changes in temperature and pressure. These reactions often result in the formation of new mineral assemblages that are stable under the prevailing metamorphic conditions. The presence of specific mineral assemblages can provide important clues about the metamorphic history of a rock. Overall, metamorphic textures provide valuable insights into the conditions and processes that have shaped Earth's crust over geological time scales. By studying these textures, geologists can reconstruct the complex history of tectonic events, mountain building processes, and crustal evolution that have occurred throughout Earth's history. Factors affecting metamorphic textures. Metamorphic textures are influenced by a variety of factors, each of which plays a crucial role in determining the characteristics of the resulting rocks. These factors can be broadly categorized into physical conditions, such as temperature and pressure, and chemical factors, including mineral composition and fluid activity. Understanding these factors is essential for interpreting the formation and evolution of metamorphic textures. Temperature. Temperature is one of the primary factors influencing metamorphic textures. As temperature increases, mineral grains may recrystallize and grow larger, leading to the development of coarser textures. Higher temperatures also promote the formation of new minerals through neocrystallization, resulting in the growth of distinct mineral assemblages characteristic of specific metamorphic facies. Pressure, both confining and differential, also plays a significant role in metamorphic texture development. Confining pressure, exerted equally from all directions, contributes to the compactness and recrystallization of minerals. Differential pressure, which varies in magnitude and direction, can lead to the development of foliation, lineation, and other textural features aligned with the direction of maximum stress. Confining environment. The depth at which metamorphism occurs affects the confining pressure, temperature, and fluid activity experienced by rocks. Deeper burial leads to higher pressures and temperatures, resulting in the formation of high-grade metamorphic rocks with distinct textures such as gneiss and schist. Conversely, rocks subjected to shallower burial experience lower-grade metamorphism and may exhibit textures like slate or phyllite. Tectonic setting. The tectonic environment in which metamorphism occurs influences the direction and magnitude of stress, which, in turn, affects the development of foliation, lineation, and other structural features. For example, rocks subjected to compressional forces in convergent plate boundaries are more likely to develop foliated textures like schist, whereas those in extensional settings may exhibit non-foliated textures such as marble. Duration of metamorphism. The duration of metamorphic conditions also influences texture development. Prolonged exposure to metamorphic conditions allows for greater mineral growth and reorganization, leading to the development of coarser textures and larger porphyroblasts. Rapid metamorphic processes, on the other hand, may result in finer-grained textures with limited mineral growth. Fluid activity. The presence of fluids, such as water-rich fluids or hydrothermal fluids, can significantly impact metamorphic textures by facilitating mineral reactions, enhancing mineral growth, and promoting the migration of ions within the rock. Fluid activity can also lead to the formation of specific mineral assemblages and the development of distinctive textures like veining, metasomatism, or retrograde metamorphic features. Original rock composition. The mineral composition and texture of the original rock, known as the protolith, influence the metamorphic reactions and textures that develop during metamorphism. Rocks with different compositions, e.g., mafic versus felsic, or textures, e.g., sedimentary versus igneous, may undergo distinct metamorphic pathways, resulting in a wide range of textures from foliated to non-foliated, and from fine-grained to coarse-grained. By considering these factors in combination, geologists can unravel the complex processes involved in metamorphism and decipher the geological history recorded in metamorphic textures. Metamorphic rocks serve as valuable archives of Earth's tectonic and geological evolution, providing insights into past environmental conditions, plate tectonic movements, and the thermal history of the Earth's crust. Textures in metamorphic rocks. Metamorphic rocks exhibit a diverse range of textures, reflecting the complex processes of mineral reorganization and recrystallization that occurred during metamorphism. These textures provide valuable information about the conditions under which the rocks formed and the subsequent tectonic and geological history they have experienced. Here, we delve into some of the most common textures found in metamorphic rocks. Foliation. Foliation is one of the most characteristic textures of metamorphic rocks and refers to the parallel alignment of mineral grains or the development of planar structures within the rock. Foliation typically results from the directed pressure or stress experienced during metamorphism, leading to the preferred orientation of platy or elongated minerals such as micas, amphiboles, and chlorite. Common types of foliation include slate cleavage, schistosity, and gneissic banding, each reflecting different degrees of metamorphic intensity and mineral alignment. Schistosity. Schistosity refers to the distinct alignment of platy minerals such as micas and chlorite, giving the rock a foliated appearance with a characteristic scaly texture. Schistosity often develops under intermediate to high-grade metamorphic conditions, where minerals recrystallize and align perpendicular to the direction of maximum stress. The presence of aligned minerals imparts a visible sheen or luster to schistose rocks, making them easily recognizable in the field. Gneissic banding. Gneissic banding is a distinctive texture characterized by alternating light and dark-colored bands of minerals within the rock. These bands typically represent layers of different mineral composition or grain size, resulting from the segregation of minerals during metamorphism. Gneissic banding often develops at high-grade metamorphic conditions and is commonly associated with regional metamorphism and the formation of continental crust during mountain-building processes. Lineation. Lineation refers to the linear arrangement of mineral grains or other features within the rock, often reflecting the direction of tectonic forces or shear during metamorphism. Lineations can take various forms, including mineral elongation, stretching lineations, or mineral alignment along shear planes. The development of lineation is particularly common in rocks subjected to intense deformation and shear, such as mylonites and ultramilonites. Porphyroblasts. Porphyroblasts are large crystals that grow within a finer-grained matrix of other minerals during metamorphism. These crystals often exhibit well-defined crystal faces and can grow to sizes visible to the naked eye. Porphyroblasts typically form under specific metamorphic conditions and can provide valuable information about the intensity and duration of metamorphic processes. Non-foliated textures. Not all metamorphic rocks exhibit foliation or preferred mineral alignment. Non-foliated metamorphic textures are common in rocks that have undergone low-grade metamorphism or recrystallization without significant deformation. Examples of non-foliated textures include granoblastic textures, where mineral grains are equidimensional and randomly oriented, and marble textures, characterized by the interlocking of calcite or dolomite crystals without distinct alignment. Migmatitic textures. Migmatites are unique metamorphic rocks that exhibit both igneous and metamorphic features, resulting from partial melting of the rock followed by crystallization. Migmatitic textures are characterized by the presence of both light-colored igneous veins or pods, leucosomes, and darker metamorphic matrix, melanosomes, giving the rock a banded or streaky appearance. Migmatites are commonly associated with high-grade metamorphic terrains and are indicative of intense metamorphic processes. These are just a few examples of the diverse textures found in metamorphic rocks, each reflecting the specific conditions and processes involved in their formation. By studying these textures, geologists can reconstruct the thermal, tectonic, and geological history of Earth's crust and gain insights into past environmental conditions, plate tectonic movements, and the evolution of mountain belts.